Good afternoon, class. We are looking at Chapter 6, Periodic and Trigonometric Functions. Here 6.3, Inverse Trigonometric Functions, Part 2. So we are looking at inverse trigonometric functions with the following objectives. Find the exact value of the expression involving the inverse sine, cosine, and tangent function. Define the inverse secant, cosecant, and cotangent function. Use a calculator to evaluate secant inverse, cosecant inverse, and cotangent inverse. Write a trigonometric expression as an algebraic expression. So reminding you of fundamental identities, here's a unit circle, x squared plus y squared equals 1, and a pair has coordinates x comma y, x is cosine and y is sine, and the relationship between tangent, sine, cosine, and so on. All trigonometric functions are periodic with a period of 2 pi, except tangent, and therefore cotangent, period of pi. All trigonometric functions are odd functions, except cosine, and therefore secant. And fundamental identities, such as Pythagorean identities, quotient identities, reciprocal identities that we have covered, and again, even and odd properties as discussed. And they are all odd except cosine, therefore secant. As far as the inverse functions are concerned, recall that all trigonometric functions are periodic, and therefore they don't have an inverse unless we do the restriction on their domain. For example, for sine, we restrict the x between negative pi over 2 and pi over 2. And now it has an inverse. Domain becomes range, range becomes domain, and the graph of the inverse looks like what you see. F inverse of f of x is x in the case of a sine. Sine inverse sine x equals x if x is between negative and positive pi over 2. F inverse of x, sine of sine inverse is x if x is between negative 1 and 2. We do the same thing for cosine. The restriction is between 0 and pi, so it gives us the inverse function. Domain becomes range, range becomes domain, and again the same thing, f inverse becomes x as long as we have the proper domain and range. In the case of cosine inverse cosine x, x must be between 0 and pi. In case of cosine inverse, then x must be between negative 1 and 1. And the same thing for tangent. It will be restricted between negative pi over 2 and pi over 2. Of course, the endpoints are not included, and now it has an inverse. Domain becomes range, range becomes domain, and tan inverse of tan x is x as long as x is between negative pi over 2 and pi over 2. Tan of tan inverse is x as long as x is between negative and positive infinity. All right. The inverse trigonometric functions, we are going to continue with the thoughts. Example 1, find the exact value of an expression involving inverse, sine, cosine, and tangent functions. Here's the example, sine of tan inverse of 1/2. And again, reminding you of what we have seen already. So remember, tan inverse is the arc or the angle. So if theta represents that, we are looking for sine theta. So there are a couple of different ways of approaching it. If tan theta is 1/2, which makes it positive, and the restriction is that theta must be negative between negative and positive pi over 2, it must belong to the first quadrant to be positive. This is positive, so it must be part of the first quadrant. And in the first quadrant, everything is positive, including sine. So tan of theta is 1/2, and we know it's y over x. And with that being the case, x is 2, y is 1, and r is square root of x squared plus y squared, reminding you that x squared plus y squared is 5 in this case because 2 squared and 1 squared. See, 2 squared plus 1 squared becomes 5. That's why r becomes square root of 5. And therefore, sine, which is y over r, is 1 over square root of 5. And by now, we know how to take care of the business here by multiplying by square root of 5 over square root of 5. We rationalize it and we make it square root of 5 over 5. And we are done. The second method uses identities. And I can say tan squared plus 1 equals secant squared. Tan is 1/2. So tan squared must be 1/4. And of course, they add up to 5/4. If secant squared is 5/4, secant is plus minus square root of 5/2, but it is positive because in the first quadrant, everything is positive. And if secant is square root of 5 over 2, that means cosine is the reciprocal of that 2 over square root of 5. And the relationship between tangent, sine, and cosine is tangent is sine over cosine. So sine is the product of these two. Remember, we want sine theta. So if we multiply tan theta, which is 1/2, by cosine, which is 2 square root of 5, we get exactly the same answer. Again, sometimes using circles may be easier, sometimes the identities, but we should be familiar with both methodologies. All right, what about this case? Example 2, cosine of sine inverse of negative 1/3. And again, sine inverse represents an arc. Let it be theta. By definition, this means we are interested in cosine theta. So if theta represents sine inverse, then sine theta must be negative 1/3. And because of the inverse function, the restriction is that we put the theta between negative pi over 2 and pi over 2, okay, which means quadrant 4 and quadrant 1. And if sine is negative, then it must belong to quadrant 4. In quadrant 4, we know cosine is positive. So we should figure out the sign on our own. And if we want to go with the circles, sine is y over r. So sine, which is negative 1/3, is y over r. R is always positive, everybody. So y is negative 1, r is 3. And remember, x squared plus y squared equals r squared. So that means x squared plus y squared equals 9. So x squared plus y squared equals 9. If y is negative 1, that means 1. It's 9. X squared is 8. And x is plus minus 2 square root of 2 or plus minus square root of 8. In the fourth quadrant, x is positive, so it becomes 2 square root of 2. Okay, that's the reason. And so if cosine is x over r, we have all the information that we want. So this is 2 square root of 2, this is 1, this is r, which is 3, and x over r means 2 square root of 3, 2 square root of 2 over 3, and that's the final answer. We can do it by the identities. We know sine squared plus cosine squared is 1. Sine is negative 1/3. Sine is negative 1/3. If I square that, I get 1 over 9. And of course, subtract it from 1, you get 8 over 9. If cosine squared is 8 over 9, and we know it to be positive, then cosine is square root of 8 over square root of 9, which is 2 square root of 2 over 3. And Perhaps in this case, the method of identities was a tad easier. Example 3, tan of cosine inverse of negative 1/3. So this represents some arc, for example, theta. That means we are looking for tan of theta. By the definition of an inverse function, if theta is cosine inverse of negative 1/3, then cosine of theta must be negative 1/3. And because we are dealing with cosine inverse, then it's between 0 and pi. That means the first and the second quadrant. Okay. In the first quadrant, cosine is positive. Because this is negative, has to be the second quadrant, in which tan is also negative. So second quadrant, tangent is negative. Now, cosine is x in the case of a unit circle, it's x over r in this case. So if it's x over r and r is always positive, then x must be negative 1. And of course, the same token, y becomes 2 square root of 2 because x squared plus y squared equals r squared negative 1. Quantity squared is 1 plus y squared is 3 squared or 9. Y squared is 8. Y is plus minus 2 square root of 2. And because it's in the second quadrant, y is positive. So in any event, tan theta is y over x. So this is negative 1. This is y. And we established y must be 2 square root of 2. Tan of theta is y over x. 2 square root of 2 over negative 1, which makes it negative 2 square root of 2. We can go with the method of identities using one of Pythagorean identities, tan squared plus 1 is secant squared. And secant squared is 9. Why is that? If cosine is negative 1/3, that means secant must be the reciprocal 3 over negative 1 or negative 3. Now, if you put it here and square it, you get 9. So tan squared is 8, and tan theta is plus minus 2 square root of 2. Tan squared is 8. Tan theta is plus minus square root of 8 or plus minus 2 square root of 2. And we know because of the quadrant, the choice must be negative. And it's always the case. Pay attention to the quadrant to make a proper decision, everybody. So this is just, in essence, looking at sine inverse, cosine inverse, tan inverse again. And now let's look at a secant function. Again, just like any other trigonometry function is periodic, it's not one-to-one. It doesn't have an inverse, so we have to do the restriction. So the restriction is that we know the domain is all real numbers. X can be 2 and plus 1 times pi over 2, and range is absolute value of y larger than or equal to 1. That means not a one-to-one function. So if we restrict it to those two, because secant is 1 over cosine, just like cosine, we go from 0 to pi with the restriction that the x can't be pi over 2. Okay, x can't be pi over 2. And then it covers all the range that is there, okay? And so we would write a couple of important and easy points. So now y equals secant inverse x, that means x equals secant y. Domain is absolute value of x is larger than or equal to 0, and range, it's between 0 and pi, and y can't be power 2. So that's the idea. And again, class, it's important to know if we have the equality. It's important to know you have to do the restriction for it to work, otherwise it doesn't. And so now let's look at those 2 points, for example. 0, 1, pi minus 1, vertical asymptote x equals power 2. So 0, 1 becomes 1, 0. This becomes negative 1 pi. Vertical asymptote changes to horizontal asymptote y equals power 2. So ultimately, it looks like this. It might be difficult to see what's happening here. Needless to say, when you graph them on the same set of axes, the two functions are inverse functions. Therefore, they must be symmetric with respect to the line y equals x, and they are. So let's find secant inverse of 2. So if we let this be theta, by definition, secant theta must be 2. Well, we know secant is 1 over cosine, and therefore cosine must be 1/2. Why do we go with cosine? It's something that we are familiar with. Cosine is 1/2. It's a common arc. Theta must be power 3. Now we are going to work on cosecant in the same manner. Again, it's not a one-to-one function. Y equals cosecant x. Domain is all real numbers. X can't be in pi, and the absolute value of y larger than or equal to 1 represents the range. It's not a one-to-one function. Because it's 1 over sine, we go with the restriction on sine, which is negative power 2 to pi over 2, those pieces. So the domain that is all real numbers, we are going to accept x can't be n pi. You say minus power 2 to power 2, of course, x can't be 0. We have now the same range. We have it a one-to-one function. Therefore, it has an inverse. So y equals cosecant inverse x. X is cosecant y. The domain, absolute value of x is larger than or equal to 0. Remember, larger than or equal to 1. Remember, domain becomes range, range becomes domain, and range y is between negative power 2 and power 2, y can't be 0. So this way, now we have a one-to-one function. Let's look at a couple of interesting points. Power 2 and 1, negative power 2 and negative 1, vertical asymptote x equal to 0. This gives us the pair 1 comma power 2. This gives us the pair negative 1 comma negative power 2. VA becomes HA, horizontal asymptote of y equal to 0. And the graph looks like that. If you put them on the same set of axes, they are, with respect to y equals x, they are inverse functions, and they're symmetric with respect to that. So, and that is the horizontal asymptote y equals 0. Now, let's look at this example. We want to find cosecant inverse of 2. So this is an arc, let it be theta or x or y or z, anything that you choose. Therefore, by definition, cosecant theta must be 2. We know cosecant is 1 over sine. If cosecant is 2, sine must be 1/2. A common arc, theta is pi over 6. So in order to find the answer for secant, we go to cosine. For cosecant, we go to sine. That is the faster way to come up with the answer. What about cotangent? The same thing. It's not a one-to-one function. When y equals cotangent, x domain is all real numbers, x can't be n pi, and it's not a one-to-one function. So what do? The restriction, because we want to have a complete cycle, we're going to go from 0 to pi because of the graph. And now that we have x between 0 and pi, it works out. It's a one-to-one function. Therefore, y equals cotangent inverse x equals cotangent y. Domain is all real numbers. That was the range there. And the range is between 0 and pi. Let's look at a couple of interesting points. 3 points. So power 4 and 1 becomes 1 power 4. Power 2, 0 becomes 0 power 2. 3 power 4, negative 1 becomes negative 1. 3 power 4. We have two vertical asymptotes. We're going to have two horizontal asymptotes. X equals 0 becomes y equals 0. X equals pi becomes y equals pi. And here's the graph. And if you put them on the same set of axes, they are symmetric with respect to the line y equals x. So if we want to find the cotangent inverse of 1, then we let theta be cotangent inverse of 1. Therefore, cotangent theta must be 1. It is a common arc. Theta must be power 4. That's the restriction 0 to pi. Approximation using calculator, and they're asking for a couple of decimals. Normally, you want to go with more unless they ask otherwise. So secant inverse of 3. What's the answer? Let's go with cosine because we are familiar with cosine. That means cosine inverse of 1/3 and definitely not a common arc. So you can put cosine inverse of 1/3 and it gives you the answer. And since they want two decimals, you stop here and it doesn't change 1.23 and we're done. Cosecant inverse of -4. Again, since we are familiar with sine, let's make it sine inverse of the reciprocal -1/4. We don't know that. It's not a common arc. So we're going to go with the calculator sine inverse of -1/4. By the way, they are in radian mode. And we want two decimals. So -0.25. Next to 5 is 2, so the 5 remains. -0.25 again, radians. Now, when it comes to cotangent, okay, something very interesting happens. First and foremost, remember cosine, the restriction is between 0 and pi, the same thing for cotangent, okay? So you can use that in case the calculator doesn't have the cotangent inverse. In fact, most calculators don't. So you deal with cosine inverse rather than cotangent inverse. I'm going to go over that concept with more details in a moment. And so what happens is that we know cotangent. So if you set this equal to theta, Set this equal to theta, that means cotangent theta is 1/2, which is x over y. So cotangent theta is x over y, which is 1/2. Cosine theta is x over r, and the r is 5 because 1 squared plus 2 squared. So first reminding you, the point has coordinates 1 and 2. So 1 squared and 2 squared, they add up to 5, so square root of 5. I'm assuming everybody knows what I'm talking about by now. X squared plus y squared is 5. So maybe I go over this in the following manner, and then I erase this. If you set this equal to theta, that means cotangent theta is equal to 1/2, okay? And since this is x over y, that means x must be 1, y must be 2, and x squared plus y squared equals 5. That's how we arrive at it. And we know cosine is x over r, so 1 over square root of 5. So in order to get to cotangent inverse of 1/2, we can use cosine inverse of 1 over square root of 5. Okay, and you use a calculator, you want 2 decimals, 0 changes to 1, you get 1.11. Now, it's important to understand. If x is positive, that means if this number is positive, everybody. Remember, positive means the first quadrant. Then you may use tan inverse of 1 over x. In this case, we can use tan inverse of 2. And they are identical, and the answer is the same. Why can't we use tangent all the time? Well, if it's negative, you can't, because tan inverse, okay, just like sine goes from negative power to power 2, but cotangent inverse goes from 0 to pi, so you cannot use tangent. You must use cosine. And there is a way around it. I'm going to go over that also. So with that being the case, as we said, this is theta. If this is equal to theta, that means cotangent theta is -2, which is x over y, -2 over 1. How do we know this is x is negative and not y? Because if cotangent is negative, from 0 to pi must be in the second quadrant. In the second quadrant, x is negative. And so you square that, you get 4. You square that, you get 1. You add them up, you get 5. And so you have the same r is square root of 5. So -2 squared 4, 1 squared 4. So you get square root of 5. So it's cosine inverse of x over r, cosine inverse of -2 over square root of 5. If you put that into a calculator, cosine inverse of -2 over 5, okay, 5 to the power of 0.5, okay. You have this one, and again, we said 2 decimals, 1 and 2. So 7, next to the 7 goes up to 8, becomes 2.68. Now, can you use tangent? Here's how it works. Given cotangent inverse of x, if x is negative, you may use tan inverse of 1 over x and then add pi. Okay. Why is that? Since tangent is negative in quadrant 4, remember, for the tangent, we use negative power 2 to power 2. If it's negative, it gives you in the quadrant 4, but cotangent is in quadrant 2, so you have to add pi. So notice, tan inverse of -1/2 gives you this one. If you add pi, gives you this one. And look at these two numbers are identical, and therefore the answer is 2.68. That's pretty interesting. So again, just a quick recap. Secant, you can go to cosine. Cosecant, you can go to sine. Cotangent, if it's positive, you can even go to tangent. Either way, cosine or tangent. Tangent is even easier. But if cotangent is negative, you have two choices. Either go to cosine or go to tangent, and whatever the answer is, you must add a pi. All right. Write a trigonometric expression as an algebraic expression, sine of tan inverse of u. And again, tan inverse of u is alpha, beta, gamma, theta. By definition, it means tan of theta is u, and we are looking for sine of that. So first, understanding what this means. Tan inverse is some angle, some arc, and we want sine of that. So if tangent is u, what is sine? That's what we are asking. Okay? And there are several ways to do so. We're going to do one of those methods. So for example, the identity 1 plus cotangent squared is cosecant squared. Cotangent, we know it to be 1 over tan squared. And cosecant, we know it to be 1 over sine squared. Why are we changing that? Because we know tangent and we want sine. So I can replace this with u squared. I can also take a common denominator here or there, it doesn't matter. So if I take a common denominator, I get tan squared plus 1 in the numerator. And so if this is 1 over sine squared, then sine squared is the reciprocal of that. And so this is u squared, this is 1 plus u squared. So there are two answers, positive and negative square root of that. However, we are looking at tan inverse, which has the same restriction as sine. And so in the first quadrant and in the fourth quadrant, so they have the same sign. In the first quadrant, both of them are positive. In this fourth quadrant, they are negative. Therefore, you don't need a plus minus because sine and tangent have the same sign. Again, because of the restriction that we put this one for the x of tangent, okay, as well as sine. And we're done with that. I want to look at a slightly different method for the sake of argument. So you see, it can be used differently. There are so many identities you may use. And so here's one way to deal with that. We've already said this is theta, and that means u equals tan theta. We already know that. And u is between negative and positive infinity. Theta is between negative power 2 and power 2. And that gives us either quadrant 1 or quadrant 4. This is the restriction we already have for the inverse function. Okay. So we want sine of tan inverse. That means we want sine of theta. So this is established already. So we can use the trick by multiplying the top and the bottom, the same thing, cosine in this case, because cosine theta over cosine theta is 1. We can do that. So if I move this underneath sine, becomes tangent theta, okay? So if you move this here, you get tan theta times cosine theta. And cosine, you can replace it with 1 over secant. So you're looking at tan over secant. Again, this is one way to do it. Because we know one of Pythagorean identities, 1 plus tan squared is secant squared, and of course, secant is the same as cosine is positive in the first and the fourth quadrant. We know that. So we have tan theta over secant theta. So what is secant theta here? Take a root. Secant theta is the square root of 1 plus tan squared. So what is tan theta, everybody? Tan theta is u. So replace it with u. So you get u over the square root of 1 plus u squared. Again, a second method. And there are more methodologies, but depends on the um, identity that you use. All right, let's continue on that thoughts. Tan of sine inverse of u, well, we let sine inverse of u be theta. By definition means sine theta is u. And so we want tan of theta. Again, remember the restriction for sine inverse is negative pi over 2 to power over 2. That's the restriction we put on its on the sine function. So we know tan theta is sine over cosine. And if sine theta is u, then cosine we can use Pythagorean identity. Sine squared plus cosine squared is 1. So this is square root of 1 minus sine squared. So this is u squared. So tan theta is u over the square root of 1 minus u squared. And again, I'm mentioning that both of them sine and tangent, as far as the inverse is concerned, they are in quadrant 1 and 4. They have the same sign, and cosine is positive. Cosine is positive. What about tan of secant inverse of u? Well, we let this be theta. Therefore, u becomes secant theta. So let's see. Let theta represent secant inverse. By definition of inverse function, u becomes secant theta. And reminding you that theta must be between 0 and pi, right? Because we're talking about secant and it follows really cosine in essence. Theta can't be pi over 2. So what are we looking for? Tan of what? Tan of theta. That's what we are looking for. And we know 1 plus tan squared is secant squared. So tan squared is secant squared minus 1. And secant can be replaced with u. So u squared minus 1. So tan theta is plus minus the square root of u squared minus 1. In the first quadrant, tangent is positive. In the second quadrant, tangent is negative. Bear in mind, the restriction on secant is from 0 to pi. Therefore, tangent can be positive or negative if it's in the first quadrant versus the second quadrant. That's why we must use plus minus. What about cosine of sine inverse of u? Well, let sine inverse be theta. And of course, because it's sine inverse, we know theta is between negative pi over 2 and pi over 2. That means quadrant 1, quadrant 4, those two quadrants. So if that is the case, that means sine of theta must be u. And so if sine of theta is u, find cosine, and we know Pythagorean identity, sine squared plus cosine squared is 1. So cosine squared is 1 minus sine squared. Cosine is square root of 1 minus sine squared, or square root of 1 minus u squared. And we know in those two quadrants, cosine is positive.